Okay, let's unpack this. Welcome back to the deep dive. This is where we take, well, stacks of sources, research technical docs, and we try to boil it all down into instant expertise for you.
And today we are focusing on one of the most foundational minds in all of modern software engineering.
We're talking about Bjarne Stroustrup, the Danish computer scientist.
The man behind C++. And, if you're touching any complex, large-scale system that needs just absolute rock-solid efficiency.
What are we talking about? Operating systems.
Oh, yeah. Operating systems, high-frequency trading platforms, game engines, mission-critical embedded systems. You are running on infrastructure that was either built with or deeply influenced by Stroustrup's work.
Exactly. So our mission today is kind of twofold. First, we're going to trace the biography, the roadmap of his journey from Denmark to the absolute innovation engine that was Bell Labs.
And second, and this is a really critical part of the deep dive, we need to understand him as an architect.
Right. We're going beyond just the history to look at the extremely precise technical details of why C++ was designed the way it was.
We're really digging into the foundational principles that let him integrate that low-level machine efficiency with, high-level abstraction. That's the magic trick.
Managing complexity.
Exactly. And the sources we've got, they just provide this incredibly detailed map of his whole journey. It's a remarkable study in strategic innovation.
We're basically pulling up the blueprints for a huge chunk of the modern software industry.
That's a good way to put it.
And before we dive into the full history, let's just let's highlight the language's original name.
Yeah.
Because it's maybe the best possible description of the design goal. It was first called C with classes.
And that name, it's just monumental in its simplicity, isn't it?
It tells you everything.
It tells you exactly the problem he was setting out to solve. I mean, C was, and it still is, the gold standard for talking directly to the metal.
Unbeatable performance.
Unbeatable performance, minimal overhead. But C was terrible for managing complexity, just awful for large-scale projects.
Right.
So Stroustrup saw this need to take the raw power of C and integrate the sort of structural safety and the design elegance of object-oriented programming.
OOP.
So it was never about replacing C, it was about elevating it.
Exactly. Elevating it to handle enterprise-level, massive complexity. And that simple addition with classes, that just set the stage for everything that came next.
It defined the whole methodology. But okay, to understand the architect, we have to start with the foundations.
You have to.
Let's begin at the start. Bjarne Stroustrup, born December 30, 1950, in Aarhus, Denmark. And our sources highlight something critical right away. His background. He came from a working-class family, attended local schools.
And that detail is more than just biography. It really contextualizes his relentless drive.
How so?
We're talking about a journey from a pretty humble provincial setting to becoming the inventor of one of the world's most influential tech tools, all developed at the absolute pinnacle of global innovation, Bell Labs.
Right. It's a story of merit, of pure intellectual focus driving this massive global impact.
So his academic foundation was laid right there in his hometown at Aarhus University. He was there from 69 to 75. And he graduates with a Candidatus Scientiarum, which is what, a 5 or 6 year degree?
Yeah, it's often considered equivalent to a master's degree in a lot of systems. His was in mathematics with computer science.
And even back then, during this, foundational period, his focus was perfectly positioned for what would eventually become C++.
Absolutely. The sources are really clear on this. His early focus areas were microprogramming and machine architecture.
Okay, let's pause on that for a second. Microprogramming isn't just coding.
No, not at all.
It's designing the hardware interface
That's
itself, right? It means knowing the absolute lowest level instructions that tell the processor how to execute tasks. Why is that specific deep knowledge so critical to the C++ philosophy?
Because Stroustrup was, at a fundamental level, completely opposed to the idea that abstraction should cost you performance.
Okay.
Many high-level languages, they rely on an interpretation layer or, lots of runtime checks, and all that adds overhead. It slows things down.
Right.
But having a deep intrinsic understanding of the microarchitecture meant he could design C++, features like classes, virtual functions that effectively compile away their overhead.
So the abstraction disappears at compile time.
Almost entirely. It ensures that when you use a C++ abstraction, the machine code that comes out the other end is nearly as fast as the hand-optimized assembly code a C programmer would write.
That's the high-performance DNA of the language.
That's it right there.
So he had the C part locked down, the deep understanding of the machine But then came the classes part, the abstraction.
And this is where a critical mentor enters his life. Kristen Nygaard.
A giant in computer science history.
A giant. Along with Ole Johan Dahl, he invented object-oriented programming with the seminal language.
And the sources clearly state that Stroustrup learned the fundamentals of OOP directly from Nygaard.
Directly. Nygaard visited Aarhus frequently, so this wasn't Stroustrup reading a textbook. This was learning OOP from the source, from the inventor.
Wow. I mean, that is a perfect fusion of intellectual training, isn't it?
It's unbelievable. He internalized the absolute necessity for speed from his machine architecture studies, and then he learned the best methodology for managing complexity OOP from the guy who came up with it.
It just perfectly sets up this lifelong tension he sought to resolve.
Which was how to get Simula's elegant safety without giving up C's raw, unadulterated speed.
And that synthesis? That explains the core design goal.
Marry the structural integrity, the inheritance, all the safety mechanisms of OOP with the direct memory access and the performance profile of C. That intellectual lineage directly dictated the entire structure of C++I.
So after Aarhus, he moves to the UK. He gets his PhD in computer science from the University of Cambridge in 1979.
His doctoral advisor was David Wheeler, another significant figure in early British computing.
But the thesis title itself is the final clue before C++ is even Spark. It was communication and control in distributed computer systems.
That title is so telling, incredibly telling.
Why?
Because distributed systems are messy, they're complex, they require just stringent resource control, reliable inter-process communication.
They demand performance.
High performance, reliability, robust ways of handling failure. So his background in systems and control wasn't just theoretical, it was aimed squarely at solving hard, real-world engineering problems.
His academic work wasn't an end in itself.
Not at all. It was preparation. It was him building the mental toolkit he'd need to build an actual tool capable of managing the next generation of massive software systems. He was focused on system architecture, resource management, complexity, long before he wrote the first line of C++.
And that's where Bell Labs comes in.
The stage was set in 1979. Right after finishing his PhD, Stroustrup joins the Computer Science Research Center of Bell Labs in Murray Hill, New Jersey.
And Bell Labs at that time wasn't just a research facility.
No, it was like a technological monastery. It's where Unix was created, where C was created, countless other foundational tools.
The perfect ecosystem for him.
Absolutely. He joined a place that was solving the world's biggest communication and systems problems right in the building where the C language itself had been forged.
And that's where he began the work that would become C++1. But let's clarify his role here. It wasn't a team effort at the start, was it?
Not at all. He made very, very strong claims about his sole architectural ownership in the early days of the language.
And the sources back this up.
They do. Stroustrup stated, and I'm quoting here, that he invented C++R, wrote its early definitions, and produced its first implementation.
So this wasn't a committee thing.
No, it was a focused, singular architectural project born out of a specific need he identified.
And he didn't stop there with the claims. He also said he chose and formulated the design criteria. He designed all its major facilities, and he was responsible for processing extension proposals in the Standards Committee.
That's a claim of total conceptual and evolutionary stewardship, from cradle to, well, global adoption.
It really speaks to the integrity of the design, doesn't it?
It does. Because he defined that core philosophy speed, direct access, elegant abstraction, he could then ensure that every new feature that was proposed later had to adhere to those initial non-negotiable criteria.
He was the guardian of the vision.
The chief guardian of the architectural vision, yeah. He made sure the language didn't just drift or, lose its performance edge in a chase for new, shiny features.
And the world got its first taste of this vision when C++ was made generally available in 1985.
A huge moment. That's when the industry really started to shift its perspective on how you could build these massive systems.
And this is where we find a really fascinating historical detail, something that just reminds you how different the computing world was back then.
Oh, yeah. The sources highlight that for non-commercial use, you could get the source code of the compiler and the foundation libraries.
The whole thing.
The whole thing, for the cost of shipping, which was a mere US $75.
$75. Just think about that. We're talking about the complete source code for a revolutionary piece of industrial-grade infrastructure.
The code that compiled the language itself?
Being distributed for basically the price of a FedEx shipment. It just reflects that that collaborative, academic, sort of pre-monetized ethos of that whole era of software.
It's so different from today, where everything is either locked down proprietary software or it's open source, relying on massive online infrastructure. Back then, sharing meant copying tapes.
Or floppy disks.
Right. And the fact that he made the source available, even for just that nominal cost, it let academics and enthusiasts get their hands on it, inspect it, learn from it.
And start using it without corporate barriers.
Which absolutely helped seed its rapid adoption.
That and the textbook. He published the first comprehensive text, the C++ programming language, in 1985. Right alongside the general release.
And that dual action is so strategic. He didn't just give people the tool, he gave them the authoritative instruction manual from the architect himself.
So programmers weren't just guessing.
No reverse engineering needed. They were immediately educated on the core design principles, which, for a language as sophisticated as C++ low, that's critical.
And this whole era at Bell Labs just cemented his status. He led their large-scale programming research department from its creation all the way until late 2002.
Over 2 decades, deeply embedded in that industrial research environment, making sure C++ evolved based on real-world needs, not just abstract theories.
That's a crucial feedback loop.
The most important feedback loop. The engineers building massive telecom infrastructure were his end users. Their problems validated the architectural choices we're about to get into.
All right. We've set up the architect's training, the environment of the invention. Now we need to spend some real time on the blueprints.
This is the heart of it.
This is the deep dive. The sources confirm that this wasn't accidental growth. It was guided architecture, carefully documented in his 1994 book, The Design and Evolution of C++ Wood, and his ACM history papers.
Absolutely. And we've got what I'd call 6 major technical pillars that really define Stroustrup's contribution. We need to look at these not just as a list of features, but as solutions.
Solutions to what?
To the pervasive problems of large-scale systems programming, memory leaks, runtime complexity, and that constant nagging tension between performance and safety.
Okay, let's start with the revolutionary part of C with classes. Pillar 1. Robust type system and semantics. Stroustrup engineered a static type system that provides equal support for built-in types and user-defined types. Why was that equality so profound?
Well, and see, if you wanted to define your own structure, let's say a point in 3D space,
Okay.
it was structurally very weak.
Okay.
The language gave you strong guarantees for an int. It knows how much memory it takes, how to copy it, all that. But for your point struct, you have to manually handle its life cycle, its copying, its cleanup.
You were on your own.
Completely. Stroustrup insisted that the custom point class you write should be a first-class citizen. It should enjoy the exact same structural safety and guarantees as a built-in int.
I can see why that's essential for scaling up. If you're writing millions of lines of code with custom classes, you need to trust the system handles them reliably.
Precisely. And to get that reliability, Stroustrup had to introduce these meticulous control mechanisms. This required control of object construction, destruction, copying, and movement.
And features like operator overloading.
Yes. This is where C++ starts to look more complex than C, but it's what makes it exponentially safer for big projects.
Okay, so walk us through that. Why is controlling construction and destruction so vital for a custom type?
Think about a custom object that wraps a resource, maybe a file handle, or a network socket, or a database connection.
Okay.
Construction, the code that runs when the object is created, needs to make sure that file is actually opened and verified. And destruction, the code that runs when the object ceases to exist, must close that file.
Right.
If the language doesn't give you a rock-solid guarantee about when and how those lifecycle hooks run, you create dangerous uncertainty. Stroustrup baked those guarantees into the core language with constructors and destructors.
And what about operator overloading, where you can redefine what, say, the plus sign means for your custom objects? That seems like a luxury.
It can seem like one, but it's really about efficiency through abstraction.
How so?
Imagine you're doing scientific computing with a big matrix class. Instead of writing matrix3.add matrix1, matrix2, you can just write matrix3 equals matrix1 plus matrix2.
Which is much more readable.
It's more readable, it's mathematically intuitive, that's the abstraction. But the compiler knows exactly what highly optimized, low-level machine instructions to generate for that matrix addition. That's the efficiency.
So the compiler just swaps the high-level symbol for the low-level process.
Exactly. You get the cleaner syntax with no runtime penalty. It's the perfect illustration of his core philosophy. Abstraction without a performance tax.
And this focus on object handling also brings us to the distinction between value and reference semantics.
A classic architectural choice. Value semantics means when you copy an object, you get a completely new, independent, deep copy of all its data.
Like making a photocopy of a document.
Perfect analogy. Changing the copy doesn't affect the original. Reference semantics, on the other hand, means you're just passing around a pointer or a handle to the original data.
Like sharing a Google Doc link.
Exactly. Any changes you make affect the one shared original.
And what did Stroustrup provide?
C++ gives the programmer the tools to define and use both efficiently. For small, simple types, value semantics, just copying the data, is fast and safe. For huge objects, copying is way too slow, so you use references or pointers reference semantics to avoid that overhead.
So he gave developers the explicit tools to choose the right model for the job.
Right. Instead of having the language force a single, often suboptimal choice on you, it's more responsibility for the programmer, but it's also maximum control.
Okay, that control over resources leads us directly from foundational types to resource safety. Pillar 2, systematic resource management. We're talking about RAII.
Resource acquisition is initialization, yes.
Why is RAII such a game changer?
RAII is Stroustrup's core answer to the problem of reliability and resource leaks, especially when errors happen. Before RAII, if you acquired a resource, say you locked a mutex or you allocated a chunk of memory,
You, the programmer, were responsible for releasing it later.
you had to manually write the cleanup code, the release log code, at the end of your function.
But what happens if an error occurs halfway through, an exception gets thrown?
Then the execution path is violently interrupted. It jumps right over your carefully written manual cleanup code, and you end up with a leaked lock, a forgotten file handle, or a memory leak. Your whole system becomes unstable.
So RAII ties the resource handling to the object lifecycle we were just talking about.
Yes. It works by having the resource acquisition, happen inside an object's constructor. That's the initialization part. And the corresponding resource release happens inside the object's destructor.
Okay.
The brilliance is that C++ guarantees that destructors are called automatically whenever an object goes out of scope.
Regardless of how it goes out of scope.
Exactly. Whether the function exits normally or through a thrown exception, the destructor is guaranteed to run.
So the language itself becomes the guaranteed cleanup crew.
That's it. It's not something the programmer has to remember to write. It's an architectural guarantee that the resource tied to that object will be released. It systematizes safety.
It shifts the burden from the fallible programmer to the infallible language rules.
And that's why C++ is trusted in environments where failure is just not an option. RAII ensures cleanup even in the face of chaos.
All right, moving beyond safety and into pure performance, the next challenge was making sure that high-level OOP structure didn't slow everything down. That's pillar 3, object-oriented efficiency.
Right. His model was based on Simula, and he included powerful features like multiple inheritance, but he had to avoid the speed penalty.
How did he do it?
He designed the efficient implementation based on virtual function tables, the V tables. This is where we get into the nuts and bolts of polymorphism. Let's say you have a class hierarchy, a base class animal and derived classes dog and cat, and you call a method like speak on a generic animal reference. The program needs to figure out at runtime whether to run the dog.speak code or the cat.speak code.
That's called dynamic dispatch.
It is, and in many older or interpreted languages, that can be slow. The system has to do a costly runtime search to find the right function.
So what did Stroustrup do?
He minimized this overhead with the virtual function table. It's basically a hidden, statically generated table of function pointers that the compiler builds for every class with virtual functions.
So instead of a slow search,
It's a single, super fast table lookup. The CPU just follows the object's hidden vtable pointer and jumps to the right function address. It's an incredibly fast operation.
so it's a form of pre-optimization done at compile time.
Exactly. The cost of abstraction is paid upfront during compilation, so the runtime penalty is minimal, just a quick indexing operation. And this efficient implementation is what allowed C++ to offer powerful OOP features while keeping the performance high enough for systems programming.
Maximum design power, minimum performance loss.
The constant trade-off solution.
That design flexibility leads perfectly into pillar 4, flexible generic programming. This is the world of templates.
Templates, specialization, concepts. Yes.
So for someone listening, why are templates a necessary innovation on top of standard OOP?
Templates solve the problem of writing the same logic over and over for different data types. Think about a simple sort function.
Okay.
You might need to sort a list of integers, a list of strings, or a list of your custom employee objects. In a language like C, you'd have to write 3 different sort functions, or use some really weak, unsafe mechanisms.
But with templates?
With templates, you write one generic algorithm.
Oh.
Template type name tsort, list T data, and it works for all of them.
It's a form of code reuse. But again, I'm guessing the C++ approach is all about compile time efficiency.
That's the absolute key distinction. Unlike generics and some other languages that might involve slower runtime casting or boxing, C++ templates are specialized by the compiler.
What does that mean, specialized?
It means if you use your template sort function on a list of integers, the compiler effectively generates a brand new, custom, highly optimized sort function specifically for integers, just as if you had written it by hand.
So you end up with super optimized binary code for every specific way you use the template.
Right. The result is 0 runtime overhead for the abstraction. Now, the trade-off is often called code bloat.
A larger executable file.
Exactly, because you have multiple specialized copies of the code,
Yeah.
but you gain maximum speed. It's a strategic choice to prioritize execution speed over binary size, which is usually the right call for performance-critical systems.
And this powerful compile time capability leads us straight into Pillar 5, compile time programming power.
Yes. Sophisticated techniques like template metaprogramming and the newer, much more accessible const_expr functions.
What does it even mean to program at compile time?
Well, imagine you need to calculate, say, the 15th Fibonacci number for something in your program, or you need to figure out the exact memory layout of a complex data structure.
Okay.
Normally, that computation happens when the program is running. At runtime, Stroustrup and the C++ community realized, wait a minute, if the inputs for a calculation are known when we're building the program, why waste CPU cycles recalculating it every single time the program runs?
That makes perfect sense. If the answer is a constant, why run the math again and again?
Precisely. And template metaprogramming was the original, let's say, esoteric way to do this. It basically tricked the template instantiation system into forcing the compiler to perform complex logic during the build process.
And the result is just embedded in the final program.
The result is embedded directly into the executable. It was incredibly powerful, but also famously cryptic and just a nightmare to write and debug.
So how did that evolve?
The introduction of const_expr functions simplified it dramatically. Const_expr lets you write a normal-looking C++ function, but if you call it with constant inputs, the compiler is guaranteed to evaluate it at compile time.
And if you call it later with a variable input,
it just executes normally at runtime. It gives you the best of both worlds.
So you get that 0 runtime cost benefit, but in a syntax that a normal developer can actually read and use.
It's a massive improvement in quality of life and performance. It allows engineers to validate complex constraints like array sizes or boundary checks during the build. If the math is wrong, the program just fails to compile.
You catch the error early.
You catch it at the earliest possible moment, shifting the workload away from the execution phase, making the final application faster and way more robust.
Incredible. Okay, finally, let's connect back to the machine. Pillar 6, low-level access and concurrency. Stroustrup made sure the language could still directly use machine and operating system resources.
And this is fundamental. This is core to C++ identity as a systems programming language. It can manipulate raw memory addresses, interface directly with hardware drivers, access specific OS kernel calls.
It's the language of choice when you can't tolerate any layer between you and the hardware.
No virtual machine, no garbage collector. That's why operating systems, device drivers, and game engines still rely on it.
And what about concurrency? The ability to run multiple threads at once. The source notes this is handled mostly through libraries, sometimes implemented using intrinsics. First, what's an intrinsic? And second, why a library-based approach? Why not bake concurrency right into the language syntax?
So intrinsics are basically special compiler-supported functions that map almost one-to-one with specific high-performance CPU instructions like atomic operations or vector processing commands.
They're the fastest way to do certain things.
The absolute fastest way. And the choice to use libraries was strategic. Concurrency models evolve very quickly. You have threading, message passing, async await.
New models are always emerging.
all the time. So by keeping the implementations in robust, high-performance libraries, rather than hard-coding one specific model into the language syntax, he kept the core language stable and independent.
And allow the libraries to evolve at their own pace.
Right. The libraries can rapidly adopt the best, fastest, intrinsic-level approaches for parallel processing as new hardware comes out. It's flexible, it's fast, and it maintains the architectural clarity of the core language.
So if we synthesize this whole section, the genius seems clear. Stroustrup solved that speed versus safety paradox by leveraging the compiler.
Yes. Leveraging the compiler to handle the complexity and the guarantees, AI templates, const texture, so that the runtime cost of abstraction is minimal, paid for during compilation.
The famous zero overhead abstraction.
Well, that's the goal. If a feature slows your code down, C++ gives you the tools to either opt out of it or to ensure the compiler can optimize it away completely.
Okay, so after architecting this incredibly complex tool, Stroustrup takes on another massive role. It's chief steward through the whole standardization process.
For 24 years, which is just an immense commitment.
Standardization can be slow, politically complex.
Especially for a language that's used across every single major industry. He was a founding member of the ANSI Committee in 1989 and then the ISO Committee in 1991. These are the bodies that officially define what C++ even means.
And he wasn't just a participant. He chaired the Evolution Working Group,
which was the subgroup responsible for reviewing and handling all proposals for language extensions. That's a huge burden.
That makes him the ultimate gatekeeper of the C++ architectural philosophy.
It does. Every new feature, from smart pointers to lambda functions, had to pass his scrutiny to make sure it upheld those core design criteria. Speed, safety, zero overhead abstraction.
That consistent leadership is a big reason why the language has maintained its rigor for, 4 decades now?
Absolutely. And all this time, his leadership at Bell Labs was continuing. He led the large-scale programming research department there until late 2002.
Which gave him that high-level industrial platform to test and inform the standardization process.
And the internal honors he got, Bell Labs Fellow, AT&T Fellow, those aren't just participation trophies. They signify that his peers and the company leadership saw his work as foundational to their entire research mission. His tool was literally building their global telecommunications infrastructure.
Then he leaves Bell Labs in 2002, and we see this fascinating shift in his career. A dual track between academia and high-end industry.
He starts with over a decade in formal academia at Texas A&M University from 2002 to 2014. He was a chair professor, then a university distinguished professor.
So he's teaching, researching, passing on the knowledge.
Exactly. But then the hybrid path really intensifies in 2014 when he takes a very visible role in an industry that's perfectly aligned with C++'s strengths.
Finance.
He joins Morgan Stanley in New York City.
And this is critical context, isn't it, for understanding the modern relevance of C++LM?
Oh, absolutely. From 2014 to 2022, he's a technical fellow and a managing director in their technology division. Wall Street is the ultimate stress test for software performance.
High-frequency trading, risk calculation.
All of it. Those data pipelines demand C++ because you need sub-millisecond control over every resource and every line of execution. Having the language's inventor advising them is a massive testament to the language's industrial necessity.
And what's really remarkable is that, at the same time, he's keeping an academic foothold as a visiting professor at Columbia University.
It's the perfect blend. He's ensuring academic rigor informs the practical application in the most demanding financial environment on the planet.
His learning loop never closed.
Never. He wasn't just observing. He was actively solving the hardest, most time-sensitive problems in global finance while refining the theoretical understanding of the tool used to solve them.
He then transitioned to a full professor at Columbia in July 2022, but his industry connection is still sharp.
It is. The sources note his current advisory role since 2021 as a technical advisor to a company called Metaspecs.
And they're focusing on a new C++ programming approach specifically for business applications.
Which confirms that the language's evolution is now shifting even more toward large-scale enterprise needs, security, stability, maintainability in these massive, complex business environments, all built on the foundation he laid 40 years ago. He is still steering that ship.
The scale of his impact is, well, it's maybe best measured by the highest honors he's received. These awards aren't just accolades. They really reflect how his contribution reshaped entire engineering disciplines.
The recognition is incredibly comprehensive. It covers engineering, computer science history, and just broader scientific achievement.
Let's start with 2018. He receives the Charles Stark Draper Prize from the U.S. National Academy of Engineering. For our listeners, why is the Draper Prize such a big deal?
It is widely regarded as the engineering equivalent of the Nobel Prize.
Wow. Okay.
So being awarded the Draper Prize for conceptualizing and developing C++, that recognizes his work as a colossal engineering feat. It's an acknowledgement that he created a tool that enabled the construction of virtually every large modern technological system.
And that same year, he got the Computer Pioneer Award from the IE Computer Society.
And that award's citation is very specific. It acknowledges him for bringing object-oriented programming and generic programming to the mainstream with his design and implementation of C++E.
Which connects perfectly back to our technical discussion.
It does. He took these powerful but kind of academic concepts like Simula's OOP and templates, and he weaponized them. He turned them into a practical industrial-strength tool that the entire industry could actually use.
And there was early validation, too. The Grace Murray Hopper Award back in 1993.
Yeah, that recognized his early work and noted that C++ was already one of the most influential programming languages in computing history.
Just 8 years after its general release.
That is an incredible pace of adoption. It just shows the immediate, profound need the industry had for a language that could deliver both that speed and that safety.
But perhaps the most telling honor for his status in the broader scientific community. In 2005, he received the William Proctor Prize for Scientific Achievement.
From Sigma Xi. And he was the first computer scientist ever to receive that award.
That's a monumental fact.
It is. It signifies the mainstream acceptance of computer science and software engineering as foundational scientific disciplines. A status earned by creating tools like C++ that showed scientific rigor being applied to complex system design.
His status is also confirmed by all the fellowships. Member of the National Academy of Engineering, Fellow of the ACM, Fellow of the IE, Fellow of the Computer History Museum.
Yeah, these fellowships place him definitively in the pantheon of computing legends, right up there with names like Knuth and Turing.
And beyond the recognition, his legacy is also defined by the definitive texts he wrote.
He didn't just build a machine, he wrote the instruction manual. 4 editions of the C++ programming language.
And we have to emphasize the annotated C++ reference manual.
Oh, that's not a beginner's guide. That is an architectural document. It provides the rationale, the deep insight into why every single feature of the language exists and behaves the way it does. It connects the design goals to the technical implementation.
And the global reach of that influence is just staggering. His books have been translated into 21 languages.
A truly universal technological footprint.
And finally, his continuous output. Over 100 academic articles and more than 100 technical reports for the C++ Standards Committee.
Right. He is constantly documenting, refining, and arguing for the future direction of the language, all based on those core founding principles. His work product is just constant.
So, synthesizing this whole deep dive, what is the ultimate conclusion we draw about Bjarne Stroustrup's contribution to technology?
I think his core achievement was solving the fundamental paradox of software engineering. Bridging that gap between low-level performance and high-level complexity management. He created a tool that guarantees raw machine speed while at the same time providing the high-level design structures, OOP, RAI, templates that you need to build software at a massive enterprise scale.
So C++ is the gold standard when you absolutely must have both safety and speed.
Yes. He took the proven speed of C and married it with the elegant safety of Simula. He gave us RAII for resource safety, templates for efficient generics, the V-table for high-speed polymorphism.
And his career itself demonstrates this unique methodology. He kept his feet firmly planted in both worlds.
Academia and the most demanding parts of industry like Bell Labs and Wall Street. And that blend ensures the language's evolution is guided by both theoretical soundness and the harshest real-world performance requirements.
It's the perfect synergy of theory and tested practice.
He taught it, he standardized it, and he used it to solve the hardest problems out there. It's the template for architectural success in computing.
Okay, so here's our final thought for you, the learner. Something for you to mull over. We've seen that Stroustrup defined these core technical areas, and he continues to advise companies on new C++ programming approaches for business applications.
Right.
So, given that modern enterprise systems are moving toward these massively parallel distributed architectures and complexity is just constantly growing, how will the core design criteria he established back in the 1980s continue to shape the next generation of software? And what new technical area might he push into the mainstream next?
It's a great question. The foundational trade-off remains eternal: speed versus complexity. Stroustrup's legacy is providing the tools to win that trade-off.
So where he focuses his advisory work is a leading indicator.
I think so. It will almost certainly indicate the next frontier in system performance engineering, my guess. It's likely centered on making complex concurrent tasks as safe and as zero overhead as RAI made sequential resource management all those decades ago.
A deep thought for a thoroughly explored subject. Thanks for joining us for this analysis of the architecture behind C++1. We'll see you next time.